I'm trying to figure out how to minimize all the different windows that I'm seeing here on the side. Seeing one speaker would be fine, but I feel like I'm blocking my own view of the screen right now. There we go. All right, so we're doing the hands-on machine learning book. This is by Aurélien Géron. Those of you who have been with us for a while know that we've been covering this book for a few months. This is the second edition of the book. He's coming out with a third one this year. And we're today discussing chapter 17, representation learning and generative learning using autoencoders and GANs. So up front, just to give the lay of the land, the main ideas that we're going to be discussing today are two methods, really. One is autoencoders, and the other is generative adversarial networks. And why are we doing these things together? Not so much because of similarities in their structure, which there are some, but also because there are similar applications for the two architectures. Autoencoders it sounds trivial when you think about it at first. The idea is that you're going to take some input vector, some machine learning, deep learning neural network, and what you want to do is you want to take an input and produce the exact same thing as output. So it would be trivial if you built your network large enough, big enough, but it becomes an interesting problem once you have some kind of bottleneck in the middle where you constrain that network so that it can only represent the data in an intermediate place using a much smaller fraction of the total amount of data. So you have to come up with some efficient, compressed form for the data. And generative adversarial networks takes a slightly different approach where you're actually, it's right in the name, you're taking two different networks and playing them against each other. And at the end of the day, the goal in both of these methods, one potential goal is to generate new data. With autoencoders, sometimes you're just going for representation learning. And there are some other objectives that you may have, such as denoising and sparsification. So the author poses an interesting question right off the bat in this chapter and says, which of the following number sequences do you find the easiest to memorize? And we look at this and we see that one of these sequences is substantially shorter than the other one. So that should be the easiest one to memorize, right? Well, we look at it and we say 40, 27, 25. There doesn't seem to be any obvious pattern. However, if you look at the other sequence, we actually see 50, 48, 46, 44. It looks like an arithmetic sequence where each one decreases by 2. So once we understand that, we can quickly look through the rest and confirm that, yes, that seems to be exactly what's going on here. So now I can say, well, to memorize this one, all I need to know is starts at 50, ends at 14, and decreased by 2 each one. So now what I have done is compressed this sequence of 20-ish numbers, 19 numbers, I think, down to a sparser representation where I only needed to know 3 numbers, really, 50, 14, and 2. I can't do that with this one. So this sequence is the one on the top is going to be much harder to memorize in spite of its shorter length. So what this comes back to is understanding how many bits do you need to represent the information that you have, and how efficiently can you represent that information. So as a different illustration, I tried to generate 5 sentences which have all about the same length, in the number of letters being used, characters being used. However, based on my lived experience, I am much better at memorizing this first sentence here, and each one becomes a little bit harder to memorize as I go down. This first one is easy to memorize both because it's a common trope, I guess, in the English language. It's supposedly one of the shortest sentences, reasonable sentences that one could construct, where you're actually using every single letter of the English alphabet. So it's a well-known sentence for that reason among English speakers. As we go down, each one of these becomes a little bit more difficult to memorize. This one here is grammatically correct, but I'm not really sure what it means. So I kind of have to remember each thing separately. I don't know what inscrutable means. It's this weird adjective to put on an animal. And the bill here, maybe it's a legislative bill, maybe it's a bill of a bird. I don't know. It's a little bit more difficult to figure out how to represent this information. As we go down to this next sentence here, these are all a bunch of English words, but now they just really make no sense, no grammatical relationship between them. So I just have to memorize this sequence of words. Going down here, maybe I can pronounce this, but I don't recognize any of these words. And then this one here, you even lose the ability to sound it out. It's like I have to memorize every single character individually. This is pretty challenging. So the next thing that the author talks about in presenting another view on how to represent data efficiently is an example from chess. And there's a study in the 1970s, I think, where it was learned that chess grandmasters were able to memorize the positions of pieces on the board. If you were just shown a board from a game, in 5 seconds, you could memorize the position of every single piece on the board. But only people who were skilled at chess could do this. People who weren't familiar with the game would have no idea. And making it more interesting, in fact, is the fact that if someone who was skilled in chess were shown a series of positions on the board, but they were something that would not realistically occur in the course of a gameplay in chess, then that would be something that, again, the chess master would have a very difficult time memorizing as well. So do chess players have far better memories than the general public? No. What we know from this study is that chess players, because they've become so well versed in the language of chess, have quickly developed the ability to represent the pertinent information from this board in a way that they can represent it in their own minds in fewer bits than the non-chess person would need in order to remember king in square b8, rook in square e8, and so forth. Once you have that experience, having played many, many games, you'll just recognize common patterns and you'll be able to memorize things in bulk much faster. So that's the idea here. And this illustration to the right is merely a neural network that is representing what this process might look like on a very small scale in the mind of the chess player. You look at these inputs coming in, you can immediately reduce them to a lower dimensional representation. And then if asked to repeat and regurgitate the entire state of the chessboard, you could then reconstruct it from your own understanding of the encodings. This is a trivialized example here, as you're only going from 3 inputs down to 2 in the latent representation and 3 in the decoder again. But in practice, for actual latent representations here, we can imagine that the dimensions of each of these things is, of course, much larger. So the author of our book, Hands-on Machine Learning here, also produced a video that I find pretty helpful on this topic several years ago. I'm not going to go play it right now, but this is just a talk about a 10-minute talk on entropy, cross entropy, and Kullback-Leibler divergence. And he presents it from the concept of understanding how to represent efficiently weather. So for instance, if we're speaking about a city like San Diego, we can perhaps guess that the weather is likely to be sunny and 70s most days. So rather than having one bit for sunny and another bit for the temperature, maybe you'll have, you'll represent sunny and 70 all in one bit, and then anything else, you might say, okay, have the other bit be a 0, and then you'll come in and have the much lower probability cases be represented with longer bit strings. So depending on the relative frequency of different possible samples in your data, you will have a different efficient representation. The most efficient way to represent the weather in San Diego will be very different from the most efficient way to represent the weather in Anchorage, Alaska, or even in Yuma, Arizona. Are there any questions on this first part? I know that we're maybe people are still muted, but I do want to allow some interaction here if possible.
Can you hear me?
Yes, please go ahead.
Okay. Can you please briefly explain about KL divergence? I have asked about this one on Slack channel. If you just mention about the concept in a brief manner. Thank you.
So KL divergence, Kullback-Leibler divergence, is a measure of the similarity, well, actually divergence. It's a difference between two probability distributions. And there's a mathematical derivation of it. We won't go into that, but I will touch on it in more detail in later when we're showing how it figures into variational autoencoders. But that's the 40,000 foot view to start.
Okay, thank you.
Hey, Robert, if I could throw in, I saw this cool description on, I think it was on Wikipedia. So if the entropy of a distribution is the number of bits, the average number of bits you need to represent something, like you were talking about, like the weather in San Diego, right? So if you have 8 equally likely values, you need 3 bits to represent them. And we're familiar with that, right? You do 0, 0, 0, 0, 0, 1, whatever. But if you have unequal things, then what you're talking about is you could maybe squeeze things, because if 99% of the time it's sunny, you just need 1 bit for that, and then you need more information for all the other cases that are only 1% of the time. But on average, you're going to get that 1 bit 99% of the time. It's going to be very compact. So I think this, first came up when people were just thinking about, like, hey, I need to send my data over my modem over the internet. What's the most I can compress it, whatever. So the cool thing is, if you think of entropy as how compact can you compress this information? What's the optimal way you can encode the information such that it would be the shortest? Then KL divergence says, if you have a distribution Y and you encoded it using the optimal encoding for X, how much longer would your data be? than if you use the actual optimal encoding for y. So I thought that was kind of a cool way of summarizing. Now, I mean, I still don't necessarily have the math of it completely down, you know, but basically if you said, for example, San Diego, I'm going to encode sunny as just the single bit 0, and all the other things are going to begin with 1, but they'll be longer. If you then use that for, I don't know, Seattle, Anchorage, whatever, someplace where it's rarely sunny, you're going to have a very inefficient representation because that short encoding is going to get very rarely used. And so KL divergence measures how much worse did you do because you used the wrong suboptimal encoding. And if you think about it that way, then if you encoded the weather in Anchorage using San Diego's best way, that's not necessarily the exact same thing as if you describe San Diego weather using Anchorage's optimal encoding. And that actually explains why KL divergence is not symmetric, that the distance from distribution 1 to 2 is not the same as the distance from 2 to 1. And I always thought it was weird that KL divergence was not symmetric, but that explanation of just if you tried to send the messages but you used the wrong encoding, at least for me, it worked.
Yeah, I think that sounds like a really helpful description, especially for understanding why it's anti-symmetric, because again, it's a bit confusing when you're learning that. Cool. So yeah, and this video actually talks a little bit about efficient bit representations as well, in the same way that Ted was just mentioning. So then we're going to move on in the book, and we get to see our first autoencoder. And an autoencoder, PCA, principal component analysis, is actually a very simple, the easiest example of an autoencoder that you can think of. And we've seen it already. We saw it in chapter 8. And you can produce PCA using a Keras style language as well. As you see here with the neural networks, we're just going to have dense layers with no activation. So we're going to build the network that we see right here, 3 input layers. We have a latent representation that will have 2 neurons after the input shape of 3. And then we'll have the decoder will give 3 outputs from an input shape of 2. And then in order to string those into a single neural network, we can take advantage of the sequential method and feed in list encoder decoder. And then in order to get the result of PCA, since that is a least squares calculation, we'll do MSE, loss. And then once you've done that, it doesn't really much matter how you optimize it, because it's a linear problem. You're going to get to it's a single convex optimization with 1 minimum, and you will get to the same result that you would if you applied PCA in a more traditional way. So because this is a network with no activations and only the 2 layers, this will run through 20 epochs in a second or a fraction thereof. And it will predict for this original 3D data set. What we're seeing is we have a plane which seems to constrain the data for the most part, but there's a little bit of variation above and below the plane. So in order to best approximate the data with one 2D surface, we get that plane, and this is what the projection will look like. So that's PCA. We're not going to stop at just the linear version of autoencoders for this chapter. We've seen neural networks can be very powerful. And so we want to see if we can improve our autoencoders by leveraging them. So here we're going to do a fully connected, dense neural network, a few layers. Again, we're going to have an encoder. And again, we're going to have a decoder. And what this one is going to be designed for is representing the data set of fashion MNIST. Fashion MNIST will be the example that we use for the duration of this chapter. Fashion MNIST, of course, we've seen this before in previous chapters. The images are 28 by 28 grayscale. And we take, usually you will, for a dense, when you're going to apply dense layers, you first of all want to flatten it into a single 784 by 1 vector. And then you can apply your dense layers in sequence. Your encoder is making each layer smaller and smaller, making that representation more compact. What we're doing here with this 30 is we're saying that we want codings in the middle that only have 30 neurons, represent the entirety of the information that was in that fashion MNIST image with just 30 neurons instead of almost 800. And then we're going to use those 30 neurons and see how well can we reconstruct that original image. And that's what we do in the decoder. We take those 30, build it back up to 100, and then back to 784. So a couple of things of note here. It's a sequential model again. The choice of loss function may be of interest. We're going to use binary cross entropy. One might consider using a regression metric such as MSE for this task. The author points out that while you could do that, because it's a grayscale where we're predicting things between 0 and 1, we actually find it's better to just choose binary cross entropy and it will converge faster. We're going to take an optimizer, stochastic gradient descent again. And then the key thing here is that we make sure to fit where the X and Y are both the same thing, because whatever the input is coming in, we want to get that same thing in the output. And then I didn't show it here, but we actually took the original train, which is 60,000 images, and we split off some of them to use as validation. So how does this dense network do? We have some original images here, and then the reconstructed outputs here. So we're looking at inputs and outputs, and not too bad, really. You're missing some features here, such as whatever this design is in, I guess this is a handbag, and you're not really seeing the edge too well. There's a lot of blurriness here. The representations, they're recognizable, but they are blurred. And the same thing with this sandal here. There's a lot of pixelation in the original. The blurred version, depending on how close you are to your screen and how well you're seeing those pixels, the blurred version might in fact look better than the original to you. So this is visualizing the images themselves. Another thing that we could do is come up with a different way of visualizing this data. What we're doing is we're looking at the input and the output, but if the point is to look at that middle latent representation, the hidden layer, how do we want to visualize that? Unlike some of the convolutional networks that we've seen where you can get these smaller and smaller representations and produce images out that look reasonable, here we're not really going to get that since we're using dense layers. The intermediate layers are going to be pretty unintelligible for any visualization of that 30-dimensional space. But what we could do is use a different dimensionality reduction algorithm, such as t-SNE, and that's what we're doing here. And what we're looking at is the 10 classes in Fashion MNIST and running a tsne to reduce it to 2 dimensions for the purposes of demonstrating it here in this slide. And you can see that the classes tend to bunch together and that there do seem to be some not only differences from one class to another, but even classes that you might think should be somewhat similar to each other are in a similar part of the space, such as the boot being near the sandal and the coats and pullovers and shirts being sort of clustered in the same area. Any questions on that before we move on?
Good so far, Robert.
I should have mentioned earlier, I'm not necessarily seeing the chat here, but if something does come up, please feel free to steer the conversation there.
All right, Ryan or I will jump in if there's a question.
Just want to mention something about this set, about which I talked about which I already said, and but maybe people didn't attend this meeting. The set is badly classified. In particular, they have a lot of women tops, which are classified rather arbitrary, I'd say. And they don't even have such class at all. At some point, when I worked with it, I even once found a mannequin, which I misclassified.
So
Yeah,
Maya, we should worry if we don't get 100% accuracy.
I didn't see anybody who would get more than 94% accuracy on this set, the classification.
Right. If you have bad images and bad labels, then you're never going to get 100%, right?
Yes. Garbage
Okay,
in, garbage
thanks.
out.
Yeah, I think you can set an upper bound, a reasonable upper bound, just using your own human classification performance. Although admittedly, that will vary from one human to another. I consider myself to be extremely ignorant in matters of fashion. So the difference between a shirt and a pullover can be a distinction that I find difficult to apply when trying to label images like this. And depending on the visibility, it can be tough to tell those from coats as well. So this is definitely a much more challenging image set than the original handwritten digits MNIST, which is the reason for its existence at all, since that digit set was pretty well mastered now by the neural network community. This is a better challenge. So you might ask, how do we train these autoencoders? And one important thing to note is that you can do what we call unsupervised pre-training. And so looking at this, the issue here is that data can be very cheap, but labels can be very expensive. So you might have lots and lots of data at hand, but you don't have labels for it. So in that case, you may not be able to train a classifier very well using your labeled data. So you might want to come up with alternatives. If you were to try to design a neural network like the one on the right and train a classifier based on a small amount of labeled data, you might find that you are overfitting your small amount of labeled data because you have a lot of parameters here in hidden layers 1 and 2 and the output. And if you don't have enough data to fit it, it just might not work so well. However, an alternative approach is presented by these autoencoders. What you could imagine instead is say, well, I think the architecture that might work for me is something like this, but I don't have enough data to prevent overfitting these hidden 1 and hidden 2 layers. Maybe what I can do is consider it as if it's the encoder half of an autoencoder. and build another layer out here, and then just try to spit back the original output. This is, so you're imagining what architecture might solve your problem. Typically, your classifiers are going to have this kind of diminishing, start from a high dimensional space and reduce it down to a low dimensional space, and eventually just a softmax for whatever your class outputs are. Now you're saying, well, maybe I can use the original data, build an autoencoder, and get these hidden 1 and hidden 2 layers sort of for free without needing any labels. And then I can come over here with these layers already trained, and then maybe I only need to train an output layer. Or maybe I tried training an output layer and it doesn't work real well, so I can unfreeze the hidden 2 layer, or I can unfreeze layers one at a time or something, but it's a much better place to start from for a task when you don't have many labels. And you can see the parallels between this and transfer learning and other problems that we've discussed in the past. A lot of times people pull a model to do an imaging problem, object detection problem. You can find the latest versions of object detection models. You can find fairly quick models like YOLO, SSD on TensorFlow Hub or other places. You can find BERT models and other NLP models on Hugging Face and other sources, and basically take advantage of somebody else who had a lot more computing power than you to get the representations of your data, and then the training that you need to do for your personal task is much shorter. So very much similar to transfer learning.
Hey, Robert, I was going to make a quick comment. So I think what you just said is very key. So for people who aren't familiar, I think this section and maybe the next couple sections where he talks about different ways to train autoencoders, we may want to go through this a little bit faster because today you're not really likely to worry about these. You're going to do transfer learning with, like you said, some Google type company that has way more compute than you. And even they still have the same problem of labels are expensive. Well, there's other techniques that people have found where they have sort of semi-supervised training techniques, or they have other approaches to handling it. And so I would say that these are no slights to Aurélien, who wrote this book, 2-3 years ago, but I think these concepts are a little less important. So maybe if we kind of speed through a little bit of this autoencoder training stuff, then we can get more to like the GANs, which I think we don't want to run out of time for those.
True. Yeah, that's a good point. We the book is 3 or 4 years old, and I built a slide deck just basically following the book. We're not really thinking too much about what has come in the time since, but yeah, it's a fast-moving field. So the next couple of things I didn't want to spend much time on anyway. There's tying weights is just the idea that you don't have to train your encoder and decoder to learn different weights in many cases, since they're inverse operations, or you can think of them as inverse operations. He shows you how you can build a dense transpose class that will tie your weights together. So you're actually using these same matrices, for encoding and decoding. Another example here is where, suppose you're trying to train an autoencoder and finding it difficult to train multiple layers at a time. This is an approach of greedy layer-wise training, which is to say, well, we start with our input, we can train one layer, maybe we can find a medium-sized representation, at least to start with, that works. Once we get one that looks good, we'll try to get another layer in here, and eventually we can take all these things together and just build this thing up one layer at a time rather than trying to train everything. This is another approach that was used a lot. You can see the 2 references here are pretty old, but now it's been kind of overcome by the advancements in training and the techniques from some of the earlier chapters, where we can train deeper networks a lot quicker and more reliably than we used to be able to. And the examples we've seen so far have just been dense networks. So here we have, we see that we can do it with the convolutional as well. And this is a very common use case, is to run with convolutional autoencoders. Convolutional is probably the single most common type of layer in GANs as well. And there's also an example shown in the Colab notebook with recurrent autoencoders, where you have an encoder LSTM and a decoder LSTM, where you're treating each row of the image as a separate sequence. So you get a couple of weird artifacts when you're doing that. You can see it's a little bit, some of these vertical lines that were occurring here just based on the sequence repetitions that you weren't getting in the other methods. Another important use for autoencoders is denoising. So here we are asking a slightly different problem. We're saying, if we have an original image, that's great, but what we'd like to be able to do is take a noisy version of that image and see if we could just start from that noisy image and recover the original image. So we train it by starting with the input, but then adding a bunch of noise and trying to train an autoencoder. A related alternative is just to throw a dropout layer in instead. And the author shows some examples from dropout here, where these are the pixel maps that are being fed into the denoising autoencoder. And the results out do look reasonably like the articles of clothing, the same 5 examples that we've been looking at. Still rather blurry, but it's gotten rid of a lot of the noise and pixelation. So variational autoencoders now are a really interesting application for autoencoders, and probably the one that may be the most difficult to understand. So this one may be worth spending a little bit of time on. So here, what we're trying to do is we are using the same autoencoder architecture, but rather than having a deterministic hidden representation producing an output like we've seen in the previous examples, what we're going to do here instead is just predict a mu and a sigma, and that will be our latent representation. So from this mu and sigma, then what we'll do while training is generate a Gaussian noise vector, one value for each of the pairs mu sigma, and we will feed that back in here with the multiplication, the addition, and we'll get an output. So what does this look like in practice? We'll have some input space here with some samples, and I assume that the colors here are some different classes on the input, and that we see them clustered into the blue, white, and red class. We're going to take this one instance here that was from the white class, and we compute using the encoder. We're going to compute a mu and sigma for it, but then what we do, rather than just use that mu and sigma and produce straight into the output, we will instead take a sample and find some other point nearby, and then that will produce the output. And what we're going to do here is we have a loss function that's going to be, there's 2 terms in this loss function. And this equation is not shown in the book, but this is from another source that I've found particularly helpful in trying to understand some of this material. A series of lectures by a professor at University of Waterloo. The link is here, and all the materials are online, as well as his videos from the course. What we have here is a loss function with basically the reconstructive loss term in the front, and the what we'll call some kind of, it's like a regularization loss term, but what it is doing is measuring this Kullback-Leibler divergence between the probability distributions. And why do we need both of these terms? You can imagine that if you did not have the second term here, what would happen when you tried to train this network? You would say, you would try to get a mu and a sigma, and you would sample, and you would quickly learn that in order to get the best reconstruction, you would want to get very close to this point here. So you'd probably learn that you want a standard deviation of basically 0 and a mu in the vicinity of the point that you're looking at. And this is great and all, but it doesn't really help us generate new samples from the original distribution. This is going to reproduce instances that look a little bit too much like our training instances. What we want is to take these representations, learn these salient features of the data set so that we can generate new instances that have those salient features, but which are different enough that they aren't necessarily tied right back to a specific instance in the training set. So what this Kullback-Leibler divergence term here is doing, and this is the equation from our book. What this term is doing is it's saying, I want to try to force these mu and sigma codings to be as close to the standard normal distribution as possible. So I recognize that that's going to give me worse reconstructions when I do so, because it's going to move my point from this one to some other point in this space here. And I'm not necessarily going to get back the same shirt that I put in, but that's the price that I'm willing to pay in order to increase the diversity of the results that I'm able to produce with this thing. Any questions so far? Comments?
Hey, Robert, quick question. So is the codings mu and sigma, is that a perturbation of a sample point or a bunch of samples?
Every sample is going to produce a different mu and sigma. So the mu and sigma are actually the representation vectors for the sample that was fed in.
Okay.
So you can imagine why are there different mu and different sigma for a given point coming in. So we just talked about the sigma being, we can't let it be 0 or else there won't be any diversity coming out. But it may be that certain instances from the training set have features, maybe some of the components of these vectors really can't be perturbed much, or they're going to look really different in the reconstruction. Whereas other components of that vector you can perturb and they're not going to affect the reconstruction as much. So these sigmas are saying for each component of the latent representation, how much am I going to allow that component to vary in order to correctly strike that balance between diversity of output and reconstruction of the original input.
Got it.
Hey, Robert, I just wanted to add, so like in the original autoencoder, if we squeeze things to just like 30 units in the middle, so basically like we're squeezing the image of 784 pixels down to like 30 floating point numbers. In this case, instead of 30 floating point numbers, it's 30 means and 30 standard deviations. And because we use sampling in this model, you don't always get exactly the mean. You get something near it, but you don't get exactly the mean. What that forces, if this model's going to work at all, you might say, well, this won't work at all. It'll just output garbage. That's one possibility. The other possibility is that all points near the mean must produce reasonable outputs that are very similar to it, which is actually the goal. That's what you're trying to do. So if I input a picture of a tabby cat, I don't want to get a dog out. I want to get a similar looking tabby cat if it's near that point. And so if this thing works at all, what you've trained it to do is to say nearby points are in the latent space are actually nearby in the conceptual space of what we see. They won't be nearby pixel wise because the pixels might be different, but conceptually they're going to be nearby. And so that's great because that means that all the tabby cats are near each other, all the Siamese cats are near each other, and then, you know, let's say the dogs, you know, the collies are near each other and the German shepherds are near each other. And so then once you have one German shepherd, you can just randomly sample from this coding space. You can randomly sample from your mean and standard deviation, and you'll get more German shepherds.
Yeah, this is sort of a stepping stone into the way that sampling will see how it's done in GANs. But in this case, we're always starting with an input image. So there's always some similarity to a particular input image. What we'll see in GANs is that we're going to be generating things from scratch only from a noise vector once we get the thing trained properly.
So Robert, quick, go ahead. Fine.
One of the things I wanted to point out is you need noise somewhere in generative setups, because if you look at the VAE here, you take some input and then you're creating some output. And if you didn't have noise anywhere, you would just always create the same sample because your weights are just fixed. So it would just always be the same thing. That noise is sort of like a seed in a certain way that it allows the model to branch off and do different things. So if you want to, you can have one input and then multiple different noises, and you can generate a whole bunch of different samples based on that. I just wanted to highlight that point because that's going to be true of any generative setup. You need some variation, otherwise it's just going to create the same sample every time.
Mm-hmm.
But Ryan, to your point, you know, neural network training is anyhow very stochastic. So, you know, unless you put the seed, which we put like a random seed, you can always change it and you can have a different sample. But if you have the same seed, yeah, I agree with you, it would get the same representation. So, Robert, to your point, like they're doing this codings at the end of hidden 2 layer. Probably they could have done it at the end of hidden 4 layer, and that would have produced a different kind of variation encoding, right?
Yeah, in theory, I think what you will find pretty universally with these kinds of models is you're gonna use the coding and inject the noise at wherever your smallest layer is. So these things usually are, you know, they start big, they get compressed because the latent representation is going to be presumably the most efficient representation you have of your data. and the place where you can get the most value by trying to do these codings. What you're hoping is that there's not a ton of correlation from one component to the next. Because this Gaussian noise vector that you're putting in if your codings have dimension 30, you're feeding it 30 independently generated Gaussian samples. So what you hope your network has learned by this point, and you hope that you've given it a small enough latent representation to force these codings to be close to independent.
Okay, yeah, I got it. Yeah, you want that thing to be as small as possible. There is a similar paper actually which talks about variational, it's called adversarial training, which actually, it adds a noise at the beginning at the input actually by perturbing the inputs by a small amount, very small amount. So that also adds like a, it's kind of a like adding a, like a dropout or just to make it more robust, the training. So it's a similar procedure if you want to add a perturbation at the beginning.
Was that in a variational autoencoder?
No, it's not a variational autoencoder, but the concept is similar. It's called virtual adversarial training. It's a paper which came out in 2017, actually. So there are two concepts, adversarial training and virtual adversarial training. Very similar to this one, actually.
Cool. Thank you for sharing. If you can link that paper in the chat, yeah. I'll check that out later.
Okay, sure, I'll do that.
So now the final third or so of the time here, we're going to spend talking about generative adversarial networks, GANs, and we can think about what the name means. Networks, they're neural networks. Adversarial means we have two networks working against each other, and generative means that we're generating some results. So the little flow chart that the author shares here is this one here. And we have two different neural networks, and we're going to be training them a little bit differently. But here's what each one's role is to do. The generator is going to generate images. It has no inputs other than just a noise vector that gets generated at the beginning that gets fed into it. It is going to try to come up with images of clothing, and it is going to try to fool the discriminator. The discriminator is going to get access to these images that the generator is producing, as well as real images from the actual training set. And the job of the discriminator is binary classification. Its job is to say, was this a real image or is this something that the generator generated? If it can tell the difference, then the generator realizes that it needs to learn how to do its job better so that it can fool the discriminator. Important to note that the generator never sees the real images directly. The only thing it sees is when it feeds fake images to the discriminator, it gets the backpropagated gradients to let it know which images seemed to fool the discriminator and how it should try to adjust its weights to give it a better chance of fooling the discriminator for these images alone. It doesn't get any feedback on the real images. So the toy example that we start with here is a we're going to have a coding size of 30. And what that means is that that's going to be the size of the noise vector that the generator is going to get. And that's what it gets as an input shape coding size. And we're just going to use dense layers for this example, although for imaging problems like this, convolutional nets are more common. And we're going to gradually grow the size of this network, 100, 150 neurons, and then 784, and reshape into an image. And the discriminator is going to be a little bit the reverse. It takes an image as input, either a real image or a fake image. It flattens it. It reduces the representation size in each layer, and eventually gets a sigmoid classification output. And the GAN itself is a sequential of the generator and the discriminator. So training GANs is a little bit more complicated than the other neural networks we've seen so far. Quite a bit more complicated, actually. That's one of the main challenges. But the nominal way to do it is to realize that we have to train the discriminator and the generator separately. So we start with, in this example here, we turn discriminator.trainable to false to start with. I think that means that we're going to, first of all, train the generator. Each epoch here, we're actually alternating. No, I guess it's training the discriminator first and then the generator. Each epoch, you see, we're alternating between training the discriminator and training the generator. One of the real challenges with training GANs is that you want your discriminator and your generator to be performing at roughly the same level. And this is more challenging than you would think. If you think about it, the discriminator's job is way easier than the generator's job. The discriminator just has to take images and say true or false, binary classification. The generator needs to learn from scratch something that will fool the discriminator. So that can be a challenge. And what happens is, in many cases, if you do this naively, you can end up with either your discriminator is outperforming your generator or your generator is outperforming your discriminator. And in neither case are you going to get very useful feedback. If your generator is just fooling the discriminator with every image that it puts in, the discriminator thinks everything is real, or just determines no difference between the two, the generator is not really going to learn how to improve itself. And the point at the end of the day is to improve the image generation. On the other hand, the more common problem is that you'll get into this thing where the discriminator will be performing better than the generator because it has the easier task. And the generator is getting, every image that it feeds in looks bad, but it's not necessarily getting super useful feedback. So one has to balance how quickly one trains. I've seen things where you run the generator through multiple times and then you train the discriminator, but you do have to do this in some sort of repeating sequence where you're training them both. You hope that they both improve at a similar rate. So this is the example here. What we're getting out of one epoch actually doesn't look too bad. We can see that some of these articles of clothing, there's definitely pixelation in them. The generator is still learning, but there's things that start to look like pullovers, things that are starting to look like trousers. It's definitely made some progress. So let's think a little bit further about the training difficulties. And we're going to look and see how this improved from epoch 1 to epoch 50. And the at the end of the day, it doesn't look like it actually improved that much. And what we see here is evidence of one of the biggest problems that you might get when training GANs. And that is a phenomenon called mode collapse. So you can imagine that the generator will, maybe it somehow stumbled on a pair of trousers early in its generation process, realized that it fooled the discriminator doing that. And then, so it says, oh, well, I need to produce something that looks like a pair of trousers. And if it learns that, it may start to try to minimize its own loss function by just producing this same class over and over again and ignoring the other classes. And we can see that's what's happening here with this example. There are some classes that are very overrepresented, the trousers, maybe the shirt, dress, there's a few of them, maybe not so overrepresented, but definitely shirts and trousers look like the two that are overrepresented. I don't see any ankle boots, bags, sneakers, sandals. Not sure there's any, I don't think there's any coats in there either necessarily. There may be a couple pullovers. Hard to tell a coat from a pullover at this resolution. So this is an issue because if we want our generator to be able to produce data that statistically resembles the original data set, we want it to be able to produce all classes from the original data set. There are a number of ways to mitigate this that are very briefly described in the text. Each of these is an interesting discussion on its own. Experience replay, mini batch discrimination, conditional generation, and being creative with the loss function are a number of ways to address this. On the next slide, I put in an example to illustrate a little bit more deep dive to see what does mode collapse look like in practice. And this actually came from the Coursera deep learning AI course on generative adversarial networks that I took sometime during 2021. And I thought this was a helpful example. So right here, what we're looking at is the generator has produced some images in an attempt to master the handwritten digit MNIST task. And it gives a 21037819. These don't look so bad to my eye, but they're clearly some issues and would be unlikely to have some squiggles like this, the cross on the 2, maybe the overlapping 0. It doesn't look so much like adult's handwriting for sure, maybe a child's handwriting in some cases. So the discriminator is going to look at these and say, well, this doesn't look like a real 2. This line through it, this 8 doesn't look so good. The 0 doesn't look so good. But you know, this 1 here is pretty convincing. This 1 is pretty convincing. The 7, that looks like it could be real. So at this point, the discriminator is going to feed that information back to the generator and say, these images were bad and these ones fooled me. And the generator, what's the generator going to learn here? Well, I think if you're looking at this data set, the generator might learn, I really need to not use curved lines because that's what's giving it away. If I put curved segments in here, the generator or the discriminator seems to pick up on me every time I'm putting in something curved. So let's just start using straight line segments instead. These things here seem to work. That one there seemed to work. So I'm just going to make line segments like that. So then the next batch that I'm going to feed to the discriminator is going to look something like this. And the discriminator is going to say, well, now they look much more like real images to me. In my real data set, I see examples of ones that are just a straight line. I also see examples of the number 1 that are built a little bit like this hangman hangman image. I also see examples of sevens like this. The discriminator probably has examples of sevens with the little dash through here from the real data set. But maybe for whatever reason, the discriminator thinks, well, this one is fake. And then the generator realizes, well, I need a vertical line segment in every image. That's what's going to fool the discriminator. So then we come down here, and what ends up happening is the generator will end up just producing a series of ones. And so this is just a deep dive into mode collapse and the phenomenon which explains it. All the different mitigation strategies, there's still research ongoing in this area, but there's been a lot of ways, including the conditional GANs, that have improved the ability of the GANs to overcome this issue and combat mode collapse. Questions on this?
You know, I taught American students college level calculus and stuff, and they didn't use to this dash at the bottom of one. They were confused by it, actually.
Yeah, I find that if I'm writing numerals and I'm writing a 1, unless I'm trying to distinguish it from written lowercase l's or something, I'm most likely going to use just this single line here, especially if it's part of a larger number. There may be certain instances that I'll try to use these other ones, but yeah, each individual is going to write these things differently. So who knows whether the image distribution of MNIST is static or not.
Oh, and they hated this dash for 7, by the way, too. I was told that it is more typical for European people or for older people.
I think I usually do the dash and the 7, come to think of it. So we're just going to touch
Robert.
on.
Yeah, no, I was going to say, take us home here.
Okay. Sure. We're just going to touch on a few examples of, we're not going to go into much detail, but some of the more recent GANs, and these even aren't the recent ones. These were just ones that were well known and at the time of the book publication 3 years ago. So deep convolutional GANs, DC GANs, take the example that we saw and use convolutional networks instead. So one of the people had been trying that for a while without too much success, and Radford and all in their paper, probably the single biggest change that they made was getting rid of the pooling layers and using stratted convolutions and transposed convolutions for the upsampling layers instead. They also got rid of, some people were still trying to use dense layers in the middle near the latent representations while convolutionals on the edges. And they settled on ReLU activations. They had more success, and I would say that these images here are a little bit more realistic looking than any of the ones that we saw in the previous training. This one here, after 50 epochs, was produced in the collab that Géron shares on his GitHub site, 50 epochs of training with his deep convolutional GAN. One of the nice things about this book and the way the code is presented here is that you really get to see the nuts and bolts, right? Almost everything is derived from scratch using low-level layers in Keras, rather than building off of existing things. So if you want to see the underlying inner workings, this is a great place to learn this concept. Pretty cool example here, which relates to some of the word representations we saw earlier. for the, in this case, what we're looking at is the DC GAN. We're sampling 3 random images that it produced where they were manually selected. This is a man wearing glasses. We found 3 other images. This is a man not wearing glasses. Found 3 other images. Here's a woman not wearing glasses. And you can do this same kind of arithmetic in the latent space that we saw in the words case with the man, woman, queen, king example. So what we're doing here is averaging the latent representations of these 3 men to get this image here. Similarly, we average these 3 latent representations, average these ones. And when you do this arithmetic, you end up with this woman in the middle here. The 8 images around the edge are just perturbations of that middle one. This is kind of a cool example of showing how the features learned in the latent representation are somewhat consistent with our own human features that we might label onto the data. Progressive growing and style GAN are the last 2 slides that I'm going to share here. And these are the last 2 little sections in the text. Progressive growing is kind of a growth out of that greedy layer-wise pre-training that we saw earlier. And here what you're doing is you're starting with a very small neural network, a 4x4 image. And what you're doing is training it so that it produces good, really low resolution images. Once it gets there, double the size, gradually incorporate the new size versus the old size. And you can build these things up this way without overwhelming your training process early. And the authors found that this was a useful way to develop high definition images that actually looked pretty good. This video demonstration here is pretty cool. I'm not going to go through it, but you can see some of the images. I recommend, if you're interested, take a look at this video here. Some of the images that they go through and the relationships between images are interesting. And lastly, the style GAN. Again, this is already 4 years old, but this is the last thing that we get to in this text. Very much a growth out of the progressive growth, the same authors that we saw in the previous slide. Here, what they're doing is using starting with the latent representations, using this mapping network, coming up with another representation W here. And the important thing about this network is that you're taking the noise input and you're producing different scales for that same noise. So this might be a very coarse image, very coarse noise up here, and very fine high frequency noise might go in a different place. And what you're doing is by adding noise separately at each stage, you can learn different types of features at different scale levels. And this was found to be really useful in generating realistic images as well. And we've got some examples down here, which is pretty cool and shows the power of these generation methods. So what we've done here on the top is we take 4 images and we've learned which parts of the latent representation correspond to gender, age, hair length, glasses, and pose. And what we can do is, using style GAN, combine these features from these individuals and all other features from these individuals on the left. So here we're gonna use, say, this man's wearing glasses, looking straight forward, and we're gonna use his age and his male gender, and we're gonna take this image and try to transform it with those features. And we get a person who is somewhat of a cross between the 2 input images that were shown originally. And we find we can use a young child here as the input, and we still get these. And now she's got much lighter complexion. We get individuals here of lighter complexion. We get another child here. In this case, that was interesting. This child actually looks pretty similar to that one, because this boy here shares many of those same features with the one on the left. But in each case, we get somebody that's combining these few features from this individual here, female gender, somewhat young age, long hair, no glasses, and we generate people with those features that otherwise share features with these people on the left. So kind of an interesting result. Another same authors produced a video of this one too, which I also highly recommend watching. That's all the content I've got. Definitely want to encourage further discussion and questions.
Yeah, nice job, Robert. You know, the thing that both the autoencoders and GANs have in common is that at some point you have a much smaller, denser, latent representation. And you know, you're doing different things in those architectures. I'll say that there's been a lot of work more recently in generative models. And so if people are interested in this, first of all, you can just go online, you can look at amazing images. You know, there's thispersondoesnotexist.com to see these amazing, completely photorealistic images that were computer generated. But then also in terms of other things, so we mentioned variational autoencoders, VAEs, we mentioned GANs. There's also now normalizing flows that people can look at. And the newest thing, which might eventually surpass GANs, are these diffusion models, denoising diffusion models. So if you're interested in generative models, those are some other keywords, some architectures you can look up.
Just kind of running through the this person does not exist, some examples here, all generated images.
Yeah, and you can see they're just so high resolution, and you know, you have
Pretty convincing.
earrings, headbands, clothing. He looks like he's about to sneeze. You even have like another person on the side of the image that got cut out. Like, what's up with that?
One of the things I'm wondering is, you know how you have the sites where people claim they look like celebrities? I'm wondering if there's a site where people claim they look like a GAN. Because that would be interesting to kind of, because some of these people, I mean, you got to imagine that even though they're computer generated, they may actually look like real people.
Right. I'll go sue this person does not exist.com and say, hey, one of those images is me.
Well, it is interesting to see how the training set affects some of the results. Many of the original papers were created using data sets such as Celeb A, and you can see how the people there's a certain look about celebs that that those images seem to capture, right?
Yeah. All right, cool. Any final questions for Robert on anything from this chapter? All right, awesome. Thanks again, Robert. And again, just a reminder, all the presenters for this are all volunteers. They gave up their time to read the chapter, to take notes, make slides, you know, look up things on the web, whatever. So, so once again, much appreciation, many kudos, and thanks, Robert. Okay, so we are at